Section 8.8 in Chapter 8 is called Y connection. That's with a W, W-Y-E, Y connection. And what we'll find in three-phase electricity in general is there are two types of connections. It's either a Y connection and a delta connection. So let's go into understanding what each one is first. Then we'll explore why we might want to connect something in one way or the other. And you know, you'll hear this, both of these terms often. It can be confusing, but there's some general things that we can take away from it and and help it make sense. But for the short term, let's dig into it. Let's see where some of these things come from. As we look at figure 8.10 again, we see that, you know, the schematic that we're looking at here, you know, these are basically three independent electrical circuits, right? And, you know, as we look at them as, you know, individually, we can view them that way. All right, so if that's the case, all right, so, you know, even if this doesn't completely make sense, just kind of go along with me for a little bit, and then I think toward the end it will. But so each, and we're gonna show, you know, that current for phase A is flowing in this direction, and that current from phase C is flowing in this direction, and current from phase B is flowing in this direction. Okay, so they all have a return path that, you know, goes from the load and back to the source. So Wilde says, why don't we get efficient here? And with these three return paths, here, here, and here, let's just all combine those return paths in one conductor. Okay? Does that make sense? I mean, you know, instead of having three separate wires, and think about this in the sense of a, you know, an industrial layout, or you know, even in transmission and distribution of electrical energy. You know, maybe, you know, if we can save that huge expense that's incurred from these additional conductors, then that would be worth doing. So for these, we can't combine, you know, the outputs to the loads, right? Because they're connected to different loads, but they all return to the same point, is what he's saying. Okay, so we can consolidate those, you know, we can consolidate all those at that point, you know, and then just branch off of them, you know. So we're going to bring all the returns into one conductor. All right, and so instead of having a three-phase 6-wire system, now we've gone to what we're going to call a three-phase 4-wire system. Okay, we've got our outputs to the loads, and then we've got the shared conductor that comes back to the common connection for the three phases there. Now, a term that you've probably heard before, but you probably didn't really know what it meant, was this term neutral. Well, this common conductor that consolidates the return paths for all three phases is known as the neutral conductor. Okay, it's known as the neutral conductor, and we'll just write it here. And as you can see, if we first look at it, you know, or you know, we can say, well, it's carrying current from phase A, and from phase B, and from phase C. And gosh, because of that, it's carrying 3 times the current that these other lines are carrying. So we need to make sure that we specify that that particular conductor has the current carrying ability that's 3 times greater than the current carrying ability of, say, this conductor, right? Or this conductor, or that conductor. But here's an interesting thing. You know, at first we'd think that the cross section would need to be 3 times that of the lines A, B, and C. But if we look at 811B, and that's what we're doing right here, if we look at 811B, and I'm going to try to find a good place to look. Well, we'll just start at the beginning. So here is phase A current, and let's color code this. This is one good thing about online. I get to use color in my figures. I think that's about the only good thing we can think about online, right? And then one more color, let's see, we'll go with green. All right, and then this would be this. Okay, so we know that the and I'll try to continue this to here, and I'll try to continue this to here. All right, so we know from earlier discussions that the voltage is 120 degrees, you know, out of phase. Well, in here too, we have 3 resistive loads. So the current and the voltage they're going to be in phase with each other for a particular phase, but in relation to the other currents, current A, B, and C will maintain this 120 degree difference. Now, it's very interesting to see that if I pick a particular point, and let me find a good point here. All right, I'm going to go here to phase C, and I'm going to say that this is 2, 4, 6, 8, 10 amps here. All right, and it's 10 amps, and let's say it's positive, so it's, you know, positive indicates a certain direction. And if I look right underneath that at that same point at 240 degrees, then what I'm going to see is that phase B is negative and phase A is negative. And it just so happens that if this were 10 amps positive in one direction, then phase B would be -5 in the opposite direction, and phase A would also be -5 in the opposite direction. So if I looked at the total current flowing at any one time, -5 plus -5 is -10. And this current we said here was 10. So the net current that's flowing at any one time is 0 at any particular instance throughout the rotation of this generator. Now, let's say I kind of went different here. He says, for example, instant currents corresponding to 240 degrees. So he picked the same place as me. I sub C is max, I sub B equals I sub A, and he says it's minus 0.5. Okay, so I said 5, he said 0.5. That would make that 1 amp. You know, if that were 0.5, 0.5, that'd be -1 plus +1 still would be 0. So we come to this idea here, this very interesting idea that, you know, if we take the phasor sum of the currents that we come up with, that the sum of the currents is going to be 0. Now, think about that for a minute. What does that get us? So what? Well, what that means is at any particular time along this curve here, the current, any time around that curve, the net current, the sum of the current, the the phasor sum of the currents is always going to be 0. Therefore, the current flowing in a balanced system at any point in a 4-wire system, the current at any point would always be 0. Now, I got something else that's mind-blowing. He says, if there's no current flowing through that conductor at any point in time, then why don't we just do away with it? And we can do that. We can actually remove this neutral conductor. And if these loads are identical, that's the requirement. They have to be identical. And we'll get into more particulars of that later. The neutral conductor is not necessarily needed. Okay? And so then he goes on to say, let's see, are we at 812? Yeah, here we go. So here is that system in place. It's composed of a generator, and you can see each phases are joined together, A, B, and C, and then you have your output lines. This one's carrying IC, this one's carrying IB, this is carrying IA, and this is connected. And so this is a 3-wire, 3-phase system. So we had 3-phase 6-wire, we had 3-phase 4-wire, and we had now a 3-phase, we had a 3-phase 3-wire system. Okay? Now, when we look at connections that are made this way, the generator and the load are said to be connected in Y. And how do we know that? Well, we know that because they all have a common connection. And that looks like a Y, an upside down Y or an upside or right side up Y. But this is a Y connection with a common point. And we've also connected the loads in a Y configuration. Now, we will get into soon why we want to connect in Y. But for right now, let's just recognize it as that common connection point. And sometimes you'll hear this Y connection called a star connection. And again, we're going to contrast Y with delta here in this chapter. Now, sometimes when we go back to this particular circuit, this three-phase 4-wire, the neutral conductor can be slightly smaller or same size as the line conductors. And this 3-phase 4-wire is used a lot in commercial industrial applications, because what we will get is we'll get a higher voltage from, say, phase A to phase C, or phase C to phase B, or phase A to phase B. But sometimes what we want is a voltage from phase to neutral, which would be a lower voltage. In our lab, we have 208 phase to phase, and the phase to neutral comes out to be 120 volts. Well, 120 volts is a very useful voltage, isn't it? We have lots of applications for that. So anyway, that's sort of our overview definition of Y. And then in the next thing, next section, we'll get into the voltage relationships, phase to phase and phase to neutral, and how they're calculated in section 8.9.